On planet X, an object falls 16 feet in 2 seconds. Knowing that the distance it falls varies directly with the square of the time of the fall, how far an object will fall in 5 seconds? In this type of problem, this still covers direct variation, but when you look closer at the problem, there entails the term square. This is a special type of direct variation, which is described as the direct square variation. The direct square variation follows the concept of exponentiation for our independent variable x. So before we could come up with our solution, let's try to describe here what is x, our independent variable, and y as our dependent variable. When you look closely at the problem, specifically in the second statement, the distance the object falls varies directly with the square of the time of the fall. The distance being mentioned here is your dependent variable, which is your y. And for your independent variable, it corresponds to the time spent the object has been falling. Now, let us try to write here the correct mathematical equation for the direct square variation. It is y is equal to kx squared. Notice the exponentiation of 2 for our independent variable square, because that corresponds to the statement varies directly as the square or with the square of the time of the fall. So we are just going to plug in all the values here with the correct and appropriate consideration of the exponentiation. So first, let's have the first pair of our independent and dependent variable. X stands for the time spent. So when you look at the first statement, an object falls 16 feet in 2 seconds. Your 2 is your independent variable, and the distance, or you could also say height, in feet is 16. That's for your first pair. Now we will be using this to get the value of k as the constant of variation or constant of proportionality, which will be used to solve the unknown. And the unknown has this pair. How far an object will fall. So we're talking about the distance or the height the object will fall. Or dependent variable, and your independent variable here is 5. So let's start with solving for k using the first pair. So y is 16 is equal to k, and then 2, but don't forget the square. It's still, again, direct variation, but more specifically direct square variation. So before we could use here the division property of equality, we would know that the square of 2 is just equal to 4. And hence, it's not 2 that we will be dividing for both sides, but it's 4. So we'll divide here as well. In short, the value of k is 16/4, or simply 4. This value will then be used to solve for the unknown using the same equation. The common mistake for some is by leaving out the exponent here, but since it's on the same problem and we will be using the same value of k, take note that it should be the same equation. So we'll be looking for y, and let's substitute here. K is 4 times x squared. Our x is 5, and you take the square of it. Using the proper process of MDAS or PEMDAS, if you would like to, the value of y is computed as 4 times 5 squared, which is 25, which will give us a result of 100. And this is y, the distance covered of an object on same planet X after 5 seconds. So we could finalize it here, and we could say the object will fall 100 feet in 5 seconds. This ends this problem. Take note, This is for direct square variation. The more you practice, the better the chance to understand math. This is a direct variation statement for math success. Let this K, the constant of variation, be this channel. In other words, the more you practice with your subscription, the better the chance to understand math. Subscribe now.